first possibility I rho divided by 2 pi a square a pi 0 2 less than rho less than some people is joining. I think it's we'll be waiting. Right. Okay, I need sorry. Okay, fine, thank you. 0 to a. The next one I divided by 2 pi rho. This is a pi. The previous class, just summary. I write you summary. Okay, summary of the previous classes. I 2 pi rho 1 minus rho square minus b square by t square plus 2 tb. This is the a pi. What is this? B less than or equal to, rho greater than or equal to b less than or equal to b plus t. The last final. Oh shit. Final. Wait. I think this is a 0. Tejaswini is joining 253. 1 bit. This is 0. 0 in this row greater than or equal to b plus t. Okay, this term we writing. First of all, graph very important. The summary you need important. This is the I plot a graph. This is the h. This is the row. Okay. First of all, first condition. The a to b h directly proportional to the row. H directly proportional to the linearly will be increases. I am writing the first one. This is the graph, linear graph. Okay. Then we can term this is the h directly proportional to row. Then the graph is a plot. This is the a. This is the I by 2 pi a. I by 2 pi a. Okay, nothing but I by 2 pi a square. I rho divided by 2 pi a square a pi. Writing. This is the first graph. Then second graph. Second one. This is nothing but h inversely proportional to 1. This is nothing. Then nothing but this distance nothing but h inversely proportional to 1 by rho. Some people is joining and please don't disturb. I'm waiting is joining. Just to time waste. Okay, please listen carefully. Next, inverse proportional slightly will decreases. This is the decreasing h inverse proportional to 1 by rho. Okay, this is nothing but I call it second conductor. This is the b. This is nothing but writing this is the cancel I by 2 pi b. 2 pi b. Then will be nothing but h inverse proportionality 1 minus something will be 0. If getting the 1, suppose this is the 1, I think again will be decreasing, then will be 0. Again will be decreasing, then 0. Again this is the decreasing. Okay, nothing but next one 0 only. Okay, this is a 0. This mode is 0. This is the graph. Okay, things understand in the graph. Okay, today topic about the is in the previous class very important. I'm expecting the semester exams. Okay, infinite long coaxial transmission line. Okay, today topic about the fourth Maxwell equation. You can derive the fourth Maxwell equation. Okay, magnetic flux density Maxwell equations. Just we can compare the electrostatic and magnetostatics. Please listen and carefully and observe the screen. Okay, what I am writing. Okay, please listen and carefully. Magnetic flux density. Maxwell equation. Okay. What is this? In the electrostatic D relation, D is equal to epsilon naught E. We know that. This is the electrostatics. Okay. What is the units? Coulomb per meter square. We know that nothing but charge per area. Okay, electric flux density, charge per area in this discuss. Okay, in this magnetic field intensity, B H relation, B is equal to mu naught H, mu H, writing mu H. Okay, where mu equal to mu naught mu R. Okay, mu naught H. Okay, what is the mu naught? This is a constant value. This is a constant. We know that in this permeability of free space. What is the units? Henry per meter. Henry per meter. We discussed already. We know that this is nothing but what is the value constant? 4 pi into 10 to the power of minus 7 Henry per meter. Okay. This is the magnetic flux. This is the magnetic flux density. This is the electric flux density. Just comparing. Okay, what is this? Epsilon, nothing but constant. Okay, this is also called constant value. You know that permittivity of free space. This is nothing but permittivity of free space. Okay, nothing but what is the value? This is the, I think we know that 8.854 10 to 4 of minus 12 or 10 to 4 of or 10 to 4 of minus 12 Faraday per meter, or else I get simplification purpose 10 to 4 of minus 9 by 36 pi. We know that. Okay. Some people is joining. It's too late. There's disturbance. Next one. This is the magnetic flux density. This is the electric flux density. Okay, we call it today electric flux and magnetic flux. Electric flux nothing but you know that electric flux. We can derive it also electric flux. Flux equal to that's electrostatic. Just comparing the electrostatics and magnetostatics. Okay, we can derive the Maxwell equations. Okay, we can find out the fourth Maxwell equation. First we can comparing, then we can find out the fourth Maxwell equation. This is a closed surface integral of d dot ds. Okay, we know that this is nothing but this flux nothing but what is this? Okay, what is the units of d? D is nothing but coulomb per meter square. Okay, this is a coulomb. Okay, in this flux. Okay, what is this in this flux? This is a magnetic flux. That is the red pen, magnetic flux. What is the magnetic flux? Nothing but in units is Weber. We know that flux density nothing but Weber per meter square. Flux passing to the area. Flux line passing to the area. Okay, we know that this flux equal to same way writing surface integral of B dot ds. B dot ds. This is the Weber. Okay, what is the unit? Unit of B is equal to we know that Weber per meter square in this situation. This is the magnetostatic field. This is the electrostatic field. Just comparing magnetic field and electric field. Okay. Then after that we discuss the magnetic flux line. First of all, I am writing magnetic flux lines due to straight wire carrying current coming out. Nothing but B is the tangential at every point on the magnetic flux line. First of all, writing the magnetic flux line. We know that electric flux line nothing but at some source point, some sink point. Electric flux line. Just comparing this electric flux line. There is no. We are using the this is a source point. This is a sink point. Okay. Every electric flux. Now positive charge to the negative charges. Positive charge to the negative charges. Okay. There is suppose there is no need. There is no need of negative charges. The flux line coming of the infinity lines. Okay, flux line coming to the infinity lines. And some source point will be there in the electrostatics, the sink point, source point, sink point. The magnetostatics, there is no need of beginning and ending point. Okay, this is a continuous charge. I think, but we are using the, suppose I taking the conductor carrying the current I. Current is flowing the steady current, nothing but DC current. Okay, we can find out the direction of magnetic field. Okay, we can find out the right direction of magnetic field. We are using the right hand thumb rule. Okay, first of all, I'm taking, this is the This is nothing but I taking this one conductor. Okay, this is the one conductor. I taking this. This is the some number of taking the flux lines. This is the this is also this is also first of all this current I. Nothing but like a conductor carrying the current I. Okay, current I. This is nothing but magnetic flux lines. This is the B magnetic flux lines in this direction, magnetic flux line. Nothing but this is the conductor. Okay, conductor carrying the current I. Okay, the steady current. We are using the right hand thumb rule. We can find out the magnetic field intensity, magnetic flux density, flux lines. Okay, in this flux line, nothing but anti-conduction. In this, there is no beginning and there is no ending point. Okay, there is no beginning and there is no ending point. In this electrostatic, there is source, there is sink will be there. Okay, and the source and sink will be there. Okay, note each flux line are closed. First of all, note each flux line are closed. Okay, what I am writing? Next one, no beginning or ending. No beginning or end. Okay, and the magnetostatic field. This is the nothing but just comparing the magnetostatic field with the electrostatic field. Just each flux line are closed path. Okay, there is no beginning, no ending. Okay, I take a conductor carrying the current I, that is steady current or a DC current. Okay, we can find the magnetic flux lines, field lines. Okay, we are using the right hand thumb rule. Okay, next one, magnetostatic field. Magnetostatic field. Not possible to have isolated magnetic charge. Magnetic poles. Nothing but isolated magnetic charge, nothing but uh, magnetic charge does not exist. The magnetostatic field isolated, note a point, it's very important. Isolated magnetic charge does not exist. Okay, isolated magnetic charge does not exist. Okay, in the electrostatic field, what we discuss, just comparing, I do the understanding. Okay, otherwise no need of understanding. That's why in comparing the electrostatic and magnetostatics. Okay, what is this electrostatic and magnetostatic? The flux equal to that is equal to the closed surface integral of d dot ds, that is equal to charge enclosed. Nothing but what is discussed in this? This is nothing but isolated charge. This is the isolated charge. Nothing but this is by using Gauss's law. Gauss's law, electric flux line not necessary closed. Nothing but we are using the take a source point and sink point. Okay, electric flux line passes to the source to sink, source to sink. That is the imaginary lines. Okay, there is the imaginary lines. That's why I am writing electric flux line are not necessary closed. Okay, this comparing electric flux line not necessary closed because there is a source will be there is a source and sink. Okay, then nothing but the gas q, nothing but isolated charge also, isolated charge. Okay, isolated charge, nothing but in this defined magnetic flux density closed surface integral of b dot ds equal to 0. Nothing but in this the closed path. Okay, that is equating the 0. Okay, in the closed b dot ds equal to 0, a total flux the closed surface equal to 0. I think is waiting for the participants. Okay, this is nothing but what I am writing. Closed surface integral of B dot ds equal to 0. Total flux to the closed surface is 0. Total flux through a closed surface is 0. Is 0. Law of surface is 0. Nothing but law of conservation of magnetic flux. We are using Gauss's law of magnetostatic field. Nothing but we take the in this pole, we take the north pole and south pole. Okay, north pole and south pole. We are using two poles. Okay, cannot be closed. Nothing but in this, nothing but we can cutting the north and south. We can divide it. North and south. We can divide. Cannot be closed. And I am telling the cannot be closed. We are using two poles. Okay, this cannot be closed. I think take a red pen. Okay, this is nothing but surface integral of b dot d is equal to 0. Think but this is the what is this? That is not in beginning point and ending point. That is equating to 0. Okay, total flux through closed surface equal to 0. Just keep it in mind. Total flux closed surface equal to 0. It's very important. Next one, Ampere's circuit law. We know that in this way we discussed the above is electrostatic and magnetostatic, electric flux and magnetic flux. Okay, we discuss in this way. Okay, Ampere's circuit law. Ampere's circuit law. We know that Ampere's law. What is this Ampere's law? Ampere's law, we derive this. Okay, with statement we know that we derive the third Maxwell equation. What is third Maxwell equation? Curl of H equal to J. Curl of H equal to J. We know that. Okay, this is the third Maxwell equation. Okay. And this derives, so closed surface integral of d dot ds equal to 0. Nothing but there is no source, no sink, there is no beginning and no ending point. Okay. Nothing but b dot ds equal to 0. Okay. There is nothing but no isolated magnetic charge. Okay. In the electrostatic, this isolated charge. Okay. This is isolated charge. This is the no isolated magnetic charge. Writing no isolated magnetic charge. Okay, please up to the screen. Isolated magnetic charge. In this comparing, this is the magnetostatics. Okay, I take a black pen. The electrostatic I writing. Electrostatic, what we will do in the second Maxwell equation? Curl of E equal to 0. Curl of E equal to 0. Nothing but this conservative nature of electric field. The curl of E vector equal to 0. This is nothing but second Maxwell equation. We know that integral form, line integral of E dot dl equal to 0. Okay. Okay, we know that this is the electrostatics. Okay, the surface integral of d dot ds equal to charge enclosed. This will discuss the electrostatics. Nothing but this is the electrostatic charge. Electrostatic charge. Okay, electrostatic charge. Okay, this is the no conservative nature of H. Nothing but in the I think it's waiting for 246 joining. Okay. Note a point. We use divergence theorem. What is the divergence theorem? Divergence theorem. Just I'm writing mathematical equation, not in the statement. That is equal to closed surface integral of approximate equal to the surface volume integral. Okay. Closed surface integral of d dot ds. Okay. Closed surface integral of d dot ds that is equal to volume integral of del dot d dv. Okay. Just I am replacing the d vector equal to b vector by simplify the fourth Maxwell equation. By we are finding the fourth Maxwell equation. That's why I am writing the d vector equal to b vector. Okay. D vector. This is the electrostatics. D is the magnetostatics. Just keep it in mind. The electric flux unit coulomb per meter square. The magnetic flux density is the Weber per meter square. Flux line passing through the area, same way but different, same way it is working. Okay. Closed surface integral of B dot ds, that is equal to volume integral of del dot B dV. Please cooperative. Please listen and carefully. Okay, dV equal dV. Okay, what is this? Closed surface integral of equating 0 in the above we discussed. This is 0. I writing volume integral of del dot B dV. Del dot B dV. Okay, I'm this what I'm writing, something is missing. Okay. Okay, fine, very good. Okay, nothing, this del dot V equal to 0. I think nothing but I writing this is the del dot B equal to 0. This is nothing but del dot B equal to 0. Del dot, okay, divergence of, okay. So magnetic field have no source, no sink point. Magnetic field lines are always continuous. Magnetic field lines are always continuous. Writing first of all, very important. Magnetic field lines are always continuous. The some 2 marks or 3 marks question, just derive the fourth Maxwell equation. Okay, this one, del dot B equal to 0. Just write down in the 2 marks. Del dot, just keep it in mind. Del dot B equal to 0, that is enough in the 2 marks. Okay, del dot B equal to 0. Just we can derive the divergence. Okay, write down the divergence theorem. We can find out the third Maxwell equation we are using. Okay, del dot B equal to 0. Magnetic field lines are always continuous. Okay, continuous. Nothing but this is the fourth Maxwell equation. I am writing this side. Fourth Maxwell equation. Field lines show magnetic field are all no source, no sink point. Magnetic field MF. Okay, no source or no beginning and no ending point. No source or no sink. Okay, field lines, no source, no sink. Just keep it in your mind. Just comparing the first one. First one. What is this first one? First Maxwell equation. We know that. Okay, del dot D equal to rho V. This is the first Maxwell equation. Okay, just comparing. Nothing but I take a D vector and B vector. This not equal to 0. Not equal to 0. The first Maxwell equation. Not equal to 0. This is equating the 0. Nothing but what is this? Magnetic field lines always continuous. Okay, this is nothing but this is not isolated charges. Electric field lines isolated charges or discontinuous. Okay, this is discontinuous. This is continuous charges. Okay, discuss. Okay, this is the fourth Maxwell equation. Just keep it in mind. Just comparing. This is the first and second. That's not equal to 0. First law Maxwell equation. Fourth law Maxwell equation. Del dot B equal to 0. Just comparing the methods. Okay. I will be just keep it in mind. Okay, I'm sending the PDF. Okay, first listen carefully. And then next topic is scalar magnetic potential. So please cooperative. I think this. And this again the next topic. Next topic. Scalar magnetic potential. We discuss about Laplace equation and Poisson's equation. Okay, Laplace equation, Poisson's equation. Just keep it in your mind. Those equations. We know that Laplace equation nothing but in the electrostatics. Okay, I think and draw this. Del square V equal to 0. Okay. Next, del square V equal to minus rho V by epsilon. Okay, this is the Poisson's equation. I writing P only. That is the Laplace equation. Okay. I think so all of you observe the screen or not. Anyone response? Are you understanding or not? I think listen carefully and observe the screen very good. Otherwise, no need. Okay, shall I continue? Okay, I continue. Scalar magnetic potential. Travia, what happened? I think is leaving and joining some unmute. What happened? Travia, are you interested in class or not? Need not interested, just leave the class. Can note the rule numbers 46. Please don't disturb. Okay, this difficulties topic, signal problem. Okay. Scalar magnetic potential. Okay, scalar magnetic potential. First of all, in this we discuss the in electrostatics and magnetostatics, this comparing methods. That is the enough. Okay, as the electrostatics, E key weak relation, as electrostatic E key weak relation is equal to minus del V, gradient of scalar potential. Del V, nothing but it is a vector differential operator. So nothing but gradient of V we discuss. Okay, that is nothing but magnitude and direction. Okay, del V. Okay, in this about topic, E key H key relation. Okay, D key B key relation. It is comparing D key B key relation. Curl of E equal to 0 we discuss the second magnetic equation. Okay, in magnetostatics, H is equal to same way, H is equal to minus of del Vm. This Vm is a magnetic scalar potential. Keep it in mind, magnetic scalar potential. Pavana is waiting and joining. Since we know that the third magnetic equation, curl of H equal to J, curl of H equal to G. What is the Vm? Vm equal to magnetic scalar potential. Okay, minus del mim. Curl of H equal to G by using this Ampere's law. Okay, Ampere's law, nothing but third magnetic equation. We are using the divergence theorem, nothing Stokes theorem. Stokes nothing but cross product. Okay, curl nothing but cross product. Okay, it's nothing but curl of H equal to 0. Curl of H equal to 0. What I am writing, please listen. Curl of H equal to 0. By writing curl of H equal to 0, in this using identity, I think I am bracket. This is carefully using identity. Curl of V equal to 0. Okay. Next, del dot curl of A vector equal to 0. Okay. So what happened in this nothing but J vector equal to curl of H equal to 0. First of all, I am writing precision. Why writing 0? Curl of H is equal to this one. I writing H is equal to minus del V. Minus del Vm. Take the cross product of minus of del Vm. H I writing this one. Okay, H is equal to minus del Vm. Okay, what is this? Curl of Vm. Nothing but curl of Vm equal to this term is 0. Identity. Curl of V equal to this term. What is the using? And this identity using curl of V equal to 0. Nothing but I writing curl of H equal to 0. Curl of H equal to 0. Curl of H equal to 0. Using identity curl of equal 0. Note, magnetic scalar potential Vm is only defined in a region where J equal to 0. Where J equal to 0, magnetic scale, I think point, note point, I am writing. Otherwise, need not understanding. First of all, note, magnetic scalar potential. Writing, please observe skill. Potential Vm. Nothing but scalar potential T. Okay, I did unit of amperes. Okay, I'll discuss why is amperes. Okay, Vm is only defined in a region where J equal to 0. J equal to 0. Okay. First of all, in this term, just keep it your box note point. This is very important. I will discuss again this note point. H vector is equal to minus del Vm. Okay. Nothing but in this term, J tries to 0. Okay. J tries to 0. Scalar potential satisfy Laplace equations. Okay. Nothing but scalar potential is equal to scalar potential, nothing but del square Vm, nothing but magnetic scalar potential. Del square Vm equal to 0. Del square Vm equal to 0. In this term, what is this? J equal to 0. Keep it box, very important. This term and this term. Okay, J equal to 0. Nothing but where we know that the fourth Maxwell equation, del dot B equal to 0. Okay, what is this B key? H relation, B equal to mu naught H. Okay, I'm writing fast. I think 5 minutes will be closed. Section, please rejoin. Please rejoin in the class. I think 45 minutes completed. Please cooperate. Please rejoining and stop sharing.